Hi and welcome back. When we're designing a stationary iterative method of this form, mxk plus 1 is nxk plus b, the crux really is in the choice of m. Now in the other core videos in this JOLT, we talked about many criteria, and here I'd like to summarize them for you. The first criterion is that m is non-singular. If m was not non-singular, then we wouldn't be able to solve this first equation. The second criterion is that that equation is really cheap to solve, and that completely depends on the choice of m. If m is triangular, we have an easy solve. If m is diagonal, we have a very easy solve. If m is the identity, we have the easiest solve of all, but we've seen that then we may not converge. So the third criterion is that m is chosen such that we do get convergence. And convergence is controlled by the amplification matrix G. And remember that G is equal to m inverse n. And what we want is that for some norm of G, the norm is smaller than 1. Now the other thing that we'd like is not just that we converge, but also that we can converge as fast as possible. And in other words, we want the rate of convergence to be as big as possible. And this rate of convergence is given by minus log 10 of the spectral radius of G. And the spectral radius is the largest eigenvalue of G in absolute value. Now you can maybe see that we have a trade-off. This is an optimization problem. If I take, for example, m equal to a, which is not a very useful extreme, then we would be extremely fast because we'd only need one iteration, but then 1 would definitely not be cheap to solve. On the other hand, if we take m is equal to the identity, then this is very cheap to solve, but we may not converge. Now, generally speaking, the more m looks like a, the faster the convergence will be. And you will see that with a lot of the very well-known iterative methods, they look for an m that has critical information of a in it. And you will see this, for example, in the core videos about a Jacobi iteration, Gauss-Seidel iteration, and also successive over-relaxation.